logistics for smaller warehouses. And of course, we've got self-driving cars are the kind of the next generation of robotics. So here's the company names for who's making it, each of these products. But this is literally like what startups are doing. This is where venture capitalists are putting their funds right now in the robotics. Actually, not all of it. There's a lot of agriculture stuff I'm not covering. There's military stuff, of course, and so on. But as far as consumer and stuff that you might like, you might encounter or have some sort of interaction with in the next decade, this is what's happening in robotics. Okay? As some of the big stories. Any comments, questions, surprises? Okay. So I really like to organize my data. Maybe that's why I'm a computer scientist. And before I had my first slide, and it was really nice and neat because I could say, well, there's a spectrum here between no autonomy or full autonomy, no autonomy, whichever way you want to go. And so I tried to go back and put all these new things that are coming out now onto a spectrum, and it didn't work. And this is a traditional spectrum that we always used in robotics, so it was kind of like, okay, wait, what's going on here? And it turns out we actually need another axis here, and that's human interaction. If we're going to look at what's coming out in the robotics field now, this element of human interaction is having humans now finally interact with robots. Changes this picture a lot. Because if I take some of our old stuff, now this was from the first slide, I'm going to put them here. I'm actually very hesitant to put the telemedicine and space exploration up here. I almost want to put them down here, and I wasn't sure. They're somewhere at this extreme. It depends on how much you consider teleoperation actual interaction. I tend to not consider it interaction. I almost want to put it there, but I think most people would disagree with me. So wherever it is, it's somewhere over here where those robots have no autonomy, those ones have full autonomy. And the new stuff that we're seeing is somewhere over there, right, where I have it highlighted. And what's really different, what's changed in the last 5 years, is that we have robots coming out to the world and interacting with people, right, in a way that is not just through teleoperation, but in such much more natural way, and they're interacting and having to work around people that were not their developers. And this is really a huge milestone. It's hard to imagine. Well, of course we're going to have robots do this. It's so obvious. But this is a major milestone we haven't been able to hit for the last 30 years of robotics. This has been hard. And of course, if you want to have your robot butler that's going to eventually do your laundry and clean your house and serve you breakfast, you need to go further up that scale where we can't go yet. Okay, but that's kind of the trend we're going. So, really quickly, I want to talk about what makes these problems hard. Why has it taken us 30 years to do this? Why haven't we seen? Why don't we have our robot butler yet, in other words? Yeah. Expensive. So for a robot butler, that is very, very critical because no one's going to buy one for their house if it costs more than their house, right? So, yeah.
Our society's not ready, and arguably still isn't. I mean, like the fact of the matter that we live in a work-based society, so these will take jobs away. There's no way around that. And so, like, you can take two options. You can create jobs elsewhere, or you can decommodify jobs.
That is very true, and it does have significant impact, especially during election season as we are right now, where elections can swing funding for these things quite significantly. And there is a lot of talk about robots taking jobs, particularly when you have pictures like this, right? Less, and even this, or even that, and Uber is famous for having their human drivers, but at the same time, now, as of last month, Uber is giving rides in autonomous cars. Now, those autonomous cars are extremely unsafe. It's ridiculous. Those humans, so there's a human driver behind the wheel, and they're intervening once every 2 minutes. It's really bad. It's a lot really high accident rate. But the company is determined to go forward with this. So but jobs is a huge, it's not what's stopping this, but it's a huge factor, yeah.
Rapid changes in technology, like the iPhone 8 is gonna be out in like 5 months instead of it just dropped a couple weeks ago.
Yes, is it gonna be that much better than the 6 or 7?
As long as it doesn't
or
blow
5?
up.
Well, that's true, it could be better than Samsung these days. Anything's better than Samsung right now. Come on. Okay, Samsung Note 7 only. Hey, I'm an Android person, so it's kind of annoying. But anyway, so technology change is huge. A lot of what drives this, actually, since we're going to talk about technology change, anyone have a guess what consumer item completely changed the field of robotics? And to help you, I'll give you the year 2010. Not that long ago. And it came out of Microsoft. Yes. Every single indoor robot has a Kinect on it. Or this, we actually prefer the Asus, that like rip-off of the Kinect. It's still, since it was an Apple bought PrimeSense and everything, whatever happened. But it was the Kinect originally, changed the field of robotics. I cannot overstate that. It's crazy. But 3D sensing, right? Cheap 3D sensing completely changed the way robots can now sense the world. Nobody predicted that. Completely made a lot of these applications possible. Not all of them, but many. Baxter has it. They might not. The delivery ones don't need it. They have an equivalent. They definitely have it. They have it as well. So within the university, almost everybody has it. All right, but anyway, going back to why this is hard. Any other thoughts? We have a lot of good ones.
The world is complicated.
The world is complicated. That's we can boil it down to that. And humans are just hard. Humans are messy. Humans all like things in their own way, and we have our unique little quirks and the way we want stuff and the kind of stuff we have in our house. Why can't all of our houses be the same, right? If they were all the same, we would have robot butlers a long time ago. But if I can take any one of these, you need to do perception. I can replace any of these pictures here, but you need perception, right? By the way, that's in the entire field of computer vision right there, right? Let's not underestimate what perception means. We need reasoning, actually reasoning about that perception data. Planning, we're pretty good at planning, but then it's really, really slow. There's all kinds of singularities we still hit, and then inevitably things go wrong, and robots are horrible error recovery except for like the most basic thing. So that's that, and this is for this, shopping domain, except shopping doesn't actually look like that. It looks like this, right, where humans just like threw stuff all over the ground, and then humans themselves are kind of crazy. Kids are really, really hard to work with, for example. They like to pretend or try to ride the robot, things like that. So I'm not kidding. This is interesting. All right, so this is why robotics is hard. This is where it is really high level. If you're talking about kind of wheeled robots, of course, humanoids are further out still. Really interesting kind of where we are right now. And so the big question that drives my lab and a lot of research labs across the country is how do we develop reliable autonomous systems that operate in human environments? Because that's really, really fun question to work on right now, because we're just at the kind of evolution of this next stage of the robotics dream. And so now talking specifically about my lab, what we try to do is work on 3 different principles, or at least these are my principles. The first thing we want is robust autonomy. Now, I realize that's a catch-all phrase. Of course, we just want, if I have robust autonomy, I've solved robotics, so it's a little too broad. But what I mean here is that we could program robots to be robust and autonomous and reason about something and do some tasks well. I'm also going to argue that that's not enough, and what we also need is learning and adaptation. And I can motivate that very, very simply and say, I can hard code that robot with whatever it needs, but if I put it into any one of your houses, you're going to not be happy with what it does, and you're going to wish for something a little different, right? You're going to want it to adapt to your needs, your environment, and the way you want things done. And so that robot needs learning and it needs adaptation. And the third thing it needs is usability. Again, sort of obvious, but this is a big one that the robotics field has largely ignored because we're so focused on these other two, trying to get navigation working or safe path planning or whatever. Usability often is like, oh, we'll add a nice interface later, it'll be fine. Turns out it's not that easy. Turns out you can write a really nice theoretical algorithm. Hint, I did this for my PhD. I wrote a really nice, theoretically sound, blah, blah, blah algorithm that worked really well in practice or when a roboticist was giving training data, and it lacked the usability. And my advisor was very smart. She said, Sonia, you only need one PhD. Do one thing. Do just focus on this. But it really frustrated me that in the end, when I later reevaluated it in terms of what I learned during my postdoc, is without that usability, if I put my nice theoretically sound algorithm in front of other people who didn't know what a support vector machine was or whatever, the way they interacted with it was not the same way, and it broke all of my nice learning, and it behaved terribly, right? And so there's this big interconnected loop here where all these things depend on each other, and if you over-focus on one and ignore the others, the overall picture that comes out is not quite what you intended. And so what my lab tries to do is look at some of these pieces and not always unite all three, but trying to look at the intersection of some of these. So I'm going to kind of highlight a couple of projects. We'll see how many we go through, but I want to talk about one that focuses on semantic reasoning, because that's a big one we're still working on right now. And then I'll talk a little bit about learning and usability. So the first project is, we started this a few years ago, and a student of mine became interested in analogical reasoning. Do you guys remember analogy questions you took in school? They look something like this, where you have a pair of words like ostrich is to bird, as cat is to feline, and you have multiple choices, right? And you have to find the pairs of words that are connected by the same analogy, right? This is a common standardized test question. And there have been some efforts on trying to answer these using computers before, but what my student was really interested in was not just answering them, but creating a machine that could explain why this analogy was valid. Why was this is the right answer? So not just give the answer, but explain why. And at a high level, what we did with these words was for each pair of words, we used something called a common sense knowledge base. So MIT has a knowledge base called ConceptNet, which was a huge effort to try to collect as much as common sense knowledge about the human world and encode it in a way that computers could read. So it has things like food, cheese is a food, and oven is used for baking pies and whatever else, right? It has just lots and lots of knowledge. And if you take any two of these words and you look for connections inside ConceptNet, that's a huge network, over 6 million nodes, you get an insane mess, but that you get information, okay, they're connected in these like 5 different ways, plus there's all this other knowledge that might be relevant. Okay, I just underestimated 5, it's more like 50. And you can prune that, we found a nice way to prune that, and you can derive connections there, and long story short, you can answer these questions. You can say, the right answer to this question is D because society is based on customs and the game is based on rules. And we could create a program that literally looked at just those pairs of words and came up with these kinds of explanations for the questions. It worked really well. It was a great elementary school student. Like a B student in middle school. It started to struggle in high school and did really badly on the SATs. Okay? SATs involve a vocabulary test, right? It's more like sanctimonious and hypocrisy maybe with erudite and so on. And words that were not any longer present in our nice crowdsourced database that we were using. So, but on the plus side, we could do well as an elementary or middle school kid. And that was a huge win. And for us, we wanted then, once we did this, to look at how can we actually use this in something more practical, because right now this is useless. This is not helping anybody to answer these multiple choice questions, right? But is there a real world application for reasoning about analogies? And so we took this framework, and remember, it just works on these pairs of words. It really doesn't need anything else. And so if we take out this whole multiple choice question, we more or less keep the rest of the reasoning. We said, okay, where else can we plug words in? And so what we did was start looking at the way robots perform tasks. Now the way we encode a task for a robot is, in many ways, there's lots of different representation, but for example, one could be more of a tree structure, right? Or you could break out a task like cooking pasta for somebody into cooking the spaghetti and cooking the sauce, right? And there's different steps to this task, and if you keep going down, it's all broken down. Now the interesting thing about robots, remember I mentioned error handling. If anything is missing here, most robots, like 99.9%, will just stop, right? If it's not in the task description, I can't find the pot, that's the end. I can't find the spoon, just stir the pasta, I give up, right? And you wouldn't have your dinner. So what we're looking at is using this kind of analogical reasoning to try to repair these plans. And to show it better, I'm going to show you a video, possibly with sound.
Pack my school bag.
Sheesh. Possibly with a lot of sound. There was a brief phrase there before. I might have killed it a little bit more than I needed to. We'll see. All right, so what happens here is we have a robot that has a task.
Can I substitute today? Yes, go ahead.
It has a plan for what it's supposed to do, pack the school bag, and it's missing an item. And what it literally does is go to this giant database of like 6 million different things and find the right thing to replace the missing item. And the way it's doing that is the same exact way we were using to answer analogy questions, by looking at the relationship between the words.
I couldn't find the pencil. Can I substitute a pen? No, that's not useful. Yes. Can I substitute a pen instead? Yes, go ahead.
Right, and so what happens when you go to a huge database and you need something to write with, you can get some strange recommendations. I'm gonna keep going here. But what it's doing in practice is looking at the word that's missing and how it relates to all the other things in the plan.
I couldn't find an apple. Can I substitute a banana? No, I don't like bananas. Can I substitute an orange instead? Sure, go ahead.
Right. So in theory, it should learn here the difference between a personal preference against bananas versus that the substitution itself was invalid. So the robot here could...
All finished. Nice job.
So here the robot could, in time, learn and refine all of these substitutions and preferences. And also what we're not doing is limiting it to any way the things it can currently see in the world, which is the obvious other stuff. And that was on purpose just to illustrate the power kind of that you get with abstract conceptual reasoning and the downfalls, right? So what it was doing is taking all the words of items and actions that it knew about, food items, office items, and so on, and saying, okay, I can't find, whatever it was, a pen, right? What do I know about pens? Well, pens are related to these things in such and such a way, and they're used for writing, and that has this property. What else has that property? Oh, quills apparently do. Great, I'll use that, right? Yeah.
Was it kind of dynamically choosing substitutes from what it knew it had, or did it see those things in the environment?
So we have a version of this that runs that is limited to things you can see or know about in this room. That's obviously a much better way in the sense that it wouldn't have these strange kind of suggestions. In this particular video, it was not doing that because we wanted to showcase what happens if you don't. Like, what if you don't know, you came to somebody's house and you wanted to replace an item with something else. It's unreasonable that you first open all of their drawers, learn everything about their house, and then make the substitution, right? There's some amount of reasoning you should be able to do without having to go rifling through somebody's entire house first. So it was kind of a give and take, but we can do that. Yeah.
So will it do a dynamic mapping when it sees all the stuff? Will it remember the stuff as is, or how does that thing work?
Yeah. So what, in terms of whether this recommendation was accepted or not?
No. In terms of actually knowing where to go.
Oh yeah. So that's linked to a semantic mapping framework, where so semantic mapping is exactly that. That it has a map of the world and it labels that with semantic information. In this case, we're cheating. We know where those objects are. I'll show you in a second, kind of phase 2 of this project, or 3 at this point, where we're actually going to be annotating and creating this semantic map at the same time as we're doing all this. And that's part of that, knowing where to look before you've even looked. Knowing that people usually keep spoons in their drawers, for example.
How did you decide the order of the replications in this video?
The order of what?
The recommendation, like the pen goes after
the connections. The connections within this graph, gigantic graph, it's a directed graph that we're searching, and the edges are weighted.
Okay.
Based on the probability of that relationship being true. And so there's a way to calculate a numerical score of likelihood that we're using. Yeah. And it's not always right, but it does a good job for the most part. So this was we had a lot of fun with this project. I also have to say that, so for those of you publishing or ever written a conference paper, I'll also let you know that so far this has been rejected twice. Okay? And one of the sticking points is that the reviewers are really uncomfortable with the fact that this relies on the robot's plan being human readable, right? Because it relies on the fact that the robot have the word glue for the thing that is looking, as opposed to object 54739, right? Which I think is a weird sticking point. And that's fine. It's actually it's in the process of getting accepted now for publication. But we've had 2 rejections, and it was annoying. And we said, fine, it doesn't have to be human readable. I can get words elsewhere. And so we moved on. As I said, we've moved on and kind of doing a second stage of this project now, and I made sure that as part of this phase, we actually have other sources of these words so that reviewers can be happy. And so the place we're getting words now is just vision, just object recognition, and saying, fine. I would assume that to know that I need another piece of, instead of tape, it would be helpful to know the word tape or glue. But I can also build a knowledge network from objects that I see in the scene. And specifically, so now we've turned the project over. It's not quite the same goals as before. What we're doing now is a little different. So again, coming back to the example of coming into someone's house, if you come into my house, okay, you're going to come over for dinner, and I'm really busy, and I'm like, oh, okay, I'm really busy storing this. Can you help me out? Can you go grab me a spoon? Right? Where are you going to look? Right? You're going to start opening drawers. Right? You're not going to go into my bathroom. That makes no sense. You could see a spoon in the sink. You probably wouldn't take it. It's dirty. Right? If you took it, you'd wash it first. Right? There's a lot of the semantic knowledge. You would probably not start looking in my refrigerator. Right? There's all this knowledge we have about where people keep things. So we kind of have a prior about this. And going back to this kind of project is we want to give robots the same prior so that robots don't have to start from scratch every time they start in a new environment. So we want them to be able to take a scene and automatically generate from a few words. So here, it's impossible to read on this projector, but this says saucepan, skillet, spaghetti, tomato, and water. Okay, imagine that these are 5 items that the robot has seen. I want it to be able to immediately, with no human intervention, to understand that, I can't even read that, something sauce, I have to read it. Have to read it over here. Used for sautéing, it wasn't sauce. So skillet, the skillet is used for sautéing. Spaghetti and tomatoes are food, and their very common location is pantries, fridges, and oh, by the way, food is edible. Water can be located in sinks and is also a food, and a lot of these things are actually generally found in kitchens, right? Now, all you've run is object recognition. The beautiful thing about this, if it works, is if all you've run is object recognition, which generates these kind of random word labels, and we can learn all kinds of interesting things immediately that can enable a robot to do a better job at whatever task it's doing. So this fall, this is currently under submission, we create a pipeline to do all that. It's actually a lot more involved than it would seem. The first thing you need to do is disambiguate word senses. So something we never think about. If I show you a cup, you think of a cup. You are not thinking of the World Cup in soccer. You are not thinking of a trophy cup or any of the other 5 or 6 or 7 or 8 definitions of the word cup. Turns out English is really annoying with the number of definitions.